we are going to see the magnetic Lorentz force. So consider a 3-dimension Cartesian coordinate system. So this can be named as z-axis, this is y and x. Let us consider the magnetic field B, uniform magnetic field B is acting along the z direction. So in the zy plane, if a charge moves with a velocity v making an angle theta with respect to magnetic field, I can draw a line which indicates the direction of the velocity of a particle plus q moving over a plane of zy at an angle of theta with respect to magnetic field B. So in such a case, what happens is, any charged particle moving with a velocity v in the presence of magnetic field will experience a kind of force, and found by a scientist whose name is Lorentz, called Lorentz force. So again I am saying that any charged particle moving with a velocity v at an angle of theta with respect to the magnetic field will experience a force is called by Lorentz by his name as magnetic Lorentz force. And some special features of a magnetic Lorentz force can be calculated, can be listed out by points. 1. If the charge is at rest, it doesn't move in the presence of uniform magnetic field, and force experienced by the charge is equal to 0. Second point, when the charge moves either parallel, just look at my finger how I move along the axis. If a charge moves along parallel to the magnetic field or anti-parallel to the magnetic field, then the force experienced by the charge is equal to 0. When exactly the force experienced by the charged particle will be maximum? If a charge moves along the y direction, that time it maintains a perpendicular angle, means 90 degree with respect to the uniform magnetic field. So when charge moves in a perpendicular manner to the uniform magnetic field, the force is equal to maximum. And fourth point is, and magnetic Lorentz force experienced by the charged particle moving in a magnetic field, F is directly proportional to the quantity of a charge which moves in the presence of magnetic field. The next point, the Lorentz force is also directly proportional to the velocity with which the charged particle moves in the presence of magnetic field. And another point, the magnetic Lorentz force is also directly proportional to the strength of the magnetic field in which it moves. So by combining all these points, we can write a equation, vector notation or vector equation. F vector is equal to Q of V cross D. So this is an equation for, or expression for, indicating the magnetic Lorentz force experienced by the charged particle moving in the presence of uniform magnetic field. Apart from the magnetic field, when you apply the electric field, then the charged particle will experience one more force due to the application of the electric field. And how will you write this same magnetic Lorentz force when electric field is also applied along with the uniform magnetic field? Very simple. You just take the Q out and add the application of the electric field as I am writing. So this is a magnetic Lorentz force experienced by the charged particle when it moves in the presence of both uniform magnetic and electric field. But our main idea is to calculate what is the force experienced due to the magnetic field. So A cross P is equal to AB sin theta. You know it very well. So when you expand this expression, so you can write F is equal to Q of VB sin theta. Arrange it alphabetically, then you will get F is equal to BQV sin theta, where theta refers the angle between the direction of the velocity of a charged particle when it moves in the presence of magnetic field to that magnetic field. The next we will move into the topic named motion of a charged particle in a uniform magnetic field. So when the charged particle moves in the presence of magnetic field, what is the path in which a charged particle can go? So it cannot be able to go in a straight line. We are going to prove that. We are going to understand that the charged particle, when it moves in the presence of magnetic field, will move in the circular path. So how come we can able to understand that most of the charged particle in the presence of magnetic field is in the form of circular path? So most of the charged particle in uniform magnetic field. Let us consider three-dimensional Cartesian coordinate system in which along the z direction uniform magnetic field is acting. Then the charged particle, namely Q, can be assumed to be in the x, and this can be y and this can be z. The charged particle can be in the xz region. Suppose if the particle moves with a velocity v in this direction in the presence of uniform magnetic field moving from top to bottom, as shown in the diagram, according to the Lorentz force, F is equal to Q of V cross B. The force acting on the particle will be perpendicular to the plane, to the direction of magnetic field and the V. So the force experienced by this charged particle should be pointed towards the center of all the three-dimensional Cartesian coordinates axis. So if this is a position of a particle and force acting along PO and perpendicular to the both the V and B, and if suppose if a particle moves, so then the particle moves like this. When a particle comes over here, then the velocity will be pointing like this. Then the magnetic field is pointing in upward direction, but force acting at this point against perpendicular to the direction of the both V and B will be pointing towards center. Similarly, in the experience of force like this and goes along the circular path, when a particle comes over here, if you name this position as R, if the velocity of a particle points in this direction, but magnetic field is always acting in the upward direction, again the force acting on the particle is perpendicular to the both V and V, so will be pointing towards the center. So whatever be the position, the particle when it reaches point Q as well as R, that the force, direction of the force experienced by the particle at all points is acting towards the center, is acting along the radius towards the center. So the particle is confined to move only in a circular path. Since the force, this particular force acts as a centripetal force on the particle, then the particle should move only in the circular path. So we can conclude by saying that any charged particle moves in the presence of magnetic field should move only along the circular path, and at all points along the circular path, the particle experiences magnetic Lorentz force which acts